So having known about cementite, ferrite, okay, and austenite, so we have a couple of more things to be known. For example, ledoberite. Okay, what is ledoberite? We know perlite, right? What is perlite? Perlite is the eutectoid mixture of ferrite and cementite. So what is ledoberite? Ledoberite is also nothing but it's a mixture of two things, that is austenite and cementite, but it is at the eutectic point. Okay, you see the phase diagram. Let us go to the phase diagram. This is the phase diagram, right? So here, okay, this is the eutectic point, and one liquid is transforming into two solids, right? One is austenite, the other one is cementite, okay, and this is a mixture of eutectic, okay, it is a eutectic mixture, okay, it is a eutectic mixture of austenite and cementite, okay, and this is called ledoberite, okay, isn't it? Right. So now it actually happens at what degree, what percentage of carbon? You have seen in the phase diagram, that is at 4.3 percentage of carbon, and it forms at, as we have seen at the eutectic reaction, that is at 1130 degrees Celsius. Okay. So ledoberite forms in a composition that is having iron with 4.3% carbon, and it happens at 1130 degrees Celsius. Okay. What about perlite? Perlite also we have seen, it happens at about 0.8 percentage of carbon, and at what temperature? Perlite, that is at 723 degrees Celsius, right? Right. Then comes the martensite. Okay. So far what we have seen, we can find out, okay, for example, austenite, ferrite, cementite, ledoberite, perlite, all these we are able to see in the phase diagram. But if you see martensite, we are talking about martensite. Before we know what it is, did we mention this in any of our phase diagram? No. Okay. And why? You will understand why we don't see it in the phase diagram only after understanding what is martensite. Okay. Martensite is nothing but it is also a solid solution of carbon in iron. Okay. In other words, solid solution of carbon in ferrite. Okay. So it is a supersaturated, we call, simply because it forms, you have lot of carbon in austenite, right? Austenite, how much maximum carbon that can go into austenite? We have seen in the just 2 slides before. It is 2%, okay, up to 2% of carbon, okay, that can go into austenite. Now, if you cool the austenite at so rapid pace, okay, at very high pace, at very high speed, okay, to low temperatures, okay, say to room temperature, okay. So what happens at high speed? The carbon that is there in austenite, okay, that is in FCC structure, does not have time to diffuse, because it has to diffuse, right, as the temperature reduces. Why it has to diffuse? Because the austenite has to be converted to ferrite, right, isn't it? That means FCC structure should be changed to BCC structure, okay, into BCC structure. In doing so, your carbon atom has to go and find another interstitial space in BCC so that it will be stable there, right? But unfortunately, what you are doing here, you are not cooling it slowly, rather you are going very fast. That means you are not giving time for the carbon to diffuse, okay. So what happens? There will be some metastable, okay, phase that will be forming, okay, or we call it a supersaturated solid solution, okay. A lot of carbon that went up to 2% that went into iron. When you cool it down, if you cool it down slowly, what happens? All the carbon will come out, right? Why? Because in ferrite, if it converts to ferrite, you have only maximum, how much carbon can go in? Only maximum 0.025. At room temperature, it is even less, right? So since carbon, lot of the 2% carbon cannot withstand, okay, cannot stand there, okay, in iron anymore, because it is changing from FCC to BCC, okay, all the remaining carbon has to come out, right? It has to diffuse out, okay. So if you go slowly, it will come out nicely, and you will still you will remain with ferrite, which is having only 0.025 carbon. All the remaining carbon will form as some other phase, okay, like cementite and so on, right? But what happens if you don't give time for carbon to diffuse, okay? So from austenite you come so fast to ferrite that there is no time for carbon to diffuse out. So in such cases you will end up with something else. It is not ferrite, but you end up with something called martensite, okay, and its crystal structure is not BCC like ferrite, it is BCT, okay, body center tetragonal, okay. So your FCC has been converted to BCT, not BCC, okay, and this BCT structure we call martensite, okay, and it has got lot of carbon in a metastable state. That is what we call, if you have more carbon in the matrix than what it can hold at the temperature, what we call, it is supersaturated solution, right? If you have more salt in water than what it can actually take, we call it supersaturated solution, right? Similarly, this martensite is a supersaturated solution of carbon, simply because it is holding carbon more than it is supposed to in equilibrium condition, okay. So it is a non-equilibrium phase, it is a metastable phase, okay, and we also call this transformation of austenite to this martensite diffusion-less transformation. Why? Because as I said, you have not given any time for the carbon atom to diffuse, okay, a long-term diffusion, maybe a short range diffusion, slight coordinated movement of atoms is there, because we are still changing the crystal structure, right, from BCC to BCT, okay, okay, but to change that you definitely need the movement of atoms. It is but very short range movement, very coordinated movement of atoms, okay. So it is easy from changing from FCC to BCT with very short range atomic movement, okay. So that is why it is converting from FCC to BCT if you don't give it time to convert to BCC ferrite, okay. So I am just repeating, summarizing, martensite is a metastable phase. It forms if you don't give time for the austenite, okay, to cool down slowly. Rather you are cooling it fast without giving any time for the carbon to diffuse out, so that you are ending up with a martensite which is called diffusion-less transformation, okay. And now what happens? What is the advantage? We actually like this martensite, okay. In engineering applications we try to have martensite, accordingly we actually do heat treatments. Like what we do, we heat it to austenitic temperature and cool it very fast, quench it, okay, so that you don't give time for carbon to diffuse out, and hence you end up with martensite, which is a diffusion-less transformation taking place, okay, and hence of course, but it is metastable, okay. What happens if you increase temperature again? This martensite will not stay, okay, it will convert to other phases, equilibrium phases. But in any case, martensite is a very important phase. We want it, it is a desirable phase in many engineering applications where you want the material to be hard, okay. So now among all these phases, okay, ferrite, cementite, okay, austenite, okay, perlite, ladoberite, okay, martensite. Martensite is the hardest phase, whereas what is the softest phase? It is the ferrite, okay. However, when I say what is the hardest phase in equilibrium diagram, iron carbide equilibrium diagram, you cannot say martensite, because I am saying equilibrium diagram, and martensite is a non-equilibrium phase. So that is why it doesn't find a place in equilibrium diagram. You see, nowhere in the diagram you see martensite, because it is coming out of some artificial fast cooling, okay, which is away from equilibrium conditions, okay. Then if you want to show martensite, if you want to understand how martensite forms, okay, for laboratory practices, you need some kind of diagrams, right? So martensite will be represented in other types of diagrams where the time factor is involved. In our phase diagrams, there is no time factor involved, right? Only composition of the alloy and the temperature, right? So that is why we have devised other type of tools like TTT diagrams or continuous cooling curves. Okay, all these diagrams that we discuss in the later subsequent slides, you see the martensite formation. Okay, because there we have time factor. So I will mention, if you go this fast, you can get martensite. If you go little slower, you get some other phase like that. Okay, so for time being, so martensite is existing only in non-equilibrium conditions. However, it is very desirable in most of the engineering practices. We try to achieve this martensite wherever required to get, if you want very hard material, okay, out of this particular steels where you have austenite at high temperatures and at low temperatures want to, rather than ferrite if you want martensite. Okay, right. So the next one, so this is where we are talking about. So all this area where you can have austenite. Okay, so when you cool it down for any of these alloy, okay, at a very fast rate, okay, you will end up with, instead of ferrite, you will end up with martensite. Okay, right. So having understood all this, so let us summarize. You have delta BCC structure, which is at very high temperature, and alpha ferrite PCC structure, and gamma that is austenite FCC structure, and Fe3C is a orthorhombic structure. Okay, right. So of course, one important thing that we, the final thing that we have to discuss about phase diagrams is the three invariant reactions taking place in the diagram. Okay, we have that are mentioned here. Okay, we have peritectic reaction, we have eutectic reaction, we have eutectoid reaction. Already we have discussed about eutectic reaction and eutectoid reaction. Okay, we have to now discuss about peritectic reaction. Okay, now we will see what they are. Okay, we know eutectic reaction, for example, happens when you have your liquid. Okay, in eutectic reaction, your liquid is transforming into two solids, that is, one is austenite, the other one is cementite, right? Whereas in eutectoid reaction, you have one solid is being transformed into two solids. Okay, you may be thinking it's only perlite. Okay, of course it's perlite, it's a mixture of two solids, right? We have mentioned here, it is actually, in fact, it is supposed to be mentioned as two solids. Okay, since perlite is a mixture of two solids, we didn't mention that. So austenite is being converted to two solids. Okay, that is eutectoid. Okay, and what is that we have not discussed about is the peritectic reaction that takes place at 1490 degrees Celsius, that is the liquid and the delta iron being transformed to one single liquid solid. In other words, one liquid plus one solid transformed to another solid, that is austenite, where it is actually happening. So let us see in iron carbon phase diagram. If you see this horizontal line, okay, you see here at the top of the horizontal line you have delta iron plus liquid, okay, and that is being transformed at this point into austenite. Okay, this is peritectic reaction that is taking place at around 1100 and odd degrees Celsius. Okay, it is in a closed look. This is the point. Okay, peritectic point. So it is happening at around this temperature, 1100 and odd degrees, and it actually converts to liquid plus delta being converted to austenite. Okay, so yeah, this is, of course, this is the left hand bottom side of the, it is a partially rendered equilibrium phase diagram, where if you want to see the ferrite, okay, see at the room temperature, the maximum carbon that can go into the iron is only 0.006 or 8%. Okay, so let us discuss the rest of the things in the next module. Okay.